Hello, hello. Oh, hi, good morning. Hi, Coffee. How are you doing? How is life going? I always get distracted by things that I do because I put the timer and I need to have the timer so that the first ad goes away. And then I forget that the timer is almost ran out. So, yes. One thing I figured out yesterday was I can increase the volume of my microphone. So I have increased the volume. I hope it's a bit higher than usual. I increased it to 150 because if it was 200, it would have been maxed out when I was speaking, which I don't like. But I hope this is more I hope there's a difference. Anyway, yes, and I hope there will be no cuts from the stream today. So here we are. Another day, another math. Here's, I saw another notification thingy at the top, and I want to see what I got. Okay, so we earned productive mastery in 15 unique skills 7 days ago, which I think I hadn't seen, and making progress just getting started, and nice listener. I'm a nice listener. Okay, that's nice. I'm glad I'm nice. And yeah, cool. Oh, is this the nice listener one? This, I have no idea. Anyway, today's goal is, I guess streaming for 2 hours is the goal. I'm not going to try to do the 2 hour and a half that I did yesterday, even though it was fine. It's just like a bit late for my normal schedule. And we continue. Unit 2, we did the quiz, but not, what is this one? Wait a second. Yeah, no. Okay. I'm right here. Number of solutions. Analyzing the number of solutions to linear equation. Didn't we watch the first video? I don't think so. But like, it was saying each. No, that was like the law of something something. Oh no. Thank you. Yesterday, it was like a planned raid. So, yeah, like it was a fully planned everything. So thank you for like acknowledging it, I guess. Because like even the raid bot was like talking about it, so I didn't mind it at all. Thank you for that. Yes. All right. I'm gonna start playing this video. I changed the location of my microphone. And I hope when I turn my head this way, you can hear me better because I don't know. But anyway, I changed the position of the microphone, and that could also lead to my voice being louder, hopefully. So, yes, I made some changes. So, I guess just any feedback would be nice. Okay. Cool. Yeah, because this is me sort of facing the microphone, and this is me not fully facing the microphone. I guess it's a good thing that it can pick up the voice at any point. But yeah, now I'm realizing the placement is probably improved. I hope so. But I am realizing it's I think it's a bit too high because I have to like sit in a good posture. Normally I would sit like a gremlin. Now I have to sit with a good posture. So that the phone can track my face. Okie dokie. Are we ready?
Determine the number of solutions for each of these equations, and they give us 3.
And now I have to, I guess I will be louder than this guy. Let's see. Number of solutions? Hold up.
Equations right over here. And before I deal with these equations in particular, let's just
Okay, audio levels very similar. That's good. Let's continue.
remind ourselves about when we might have one or infinite or no solutions. You're going to have one solution if you can, by solving the equation, come up with something like x is equal to some number. Let's say x is equal to, if I want to say in the abstract, x is equal to a, or if we actually were to solve it, we get something like x equals 5 or 10 or negative pi, whatever it might be. But if you could actually solve for a specific x, then you have one solution. So this is one solution. Just like that. Now, if you go and you try to manipulate these equations in completely legitimate...
Hold up, are we saying we have cases where x is multiple, has multiple solutions? Or like anywhere between this and that would work?
ways, but you end up with something crazy like 3 equals 5, then you have no solutions. No solutions. And if you just think about it reasonably, all of these are...
That would be not an equation.
Equations are about finding an x that satisfies this. And if you were to just keep simplifying it and you were to get something like 3 equals 5, and you were to ask yourself the question, is there any x that can somehow magically make 3 equal 5? No, no x can magically make 3 equal 5, so there's no way that you can make this thing be actually true, no matter which x you pick. So if you get something very strange like this...
Hi Abid. Good morning. On my side. How are you doing? How are classes going?
This means there's no solution. On the other hand, if you get something like 5 equals 5, and I'm just overusing the number 5. It didn't have to be the number 5. It could be 7 or 10 or 113, whatever. And actually, let me just not use 5 just to make sure that you don't think it's only for 5. If I just get something that something is equal to itself, which is just going to be true, no matter what x you pick, any x you pick, this would be true for, well, then you have an infinite solutions. So with that as a little bit of a primer, let's try to tackle these 3 equations. So over here, let's see, maybe we could...
Oops, I didn't know I still have ReadyBot. Cool. I'm gonna have to murder it later. Cool. Anyway.
Subtract, if we want to get rid of this 2 here on the left-hand side, we could subtract 2 from both sides. If we subtract 2 from both sides, we are going to be left with, on the left-hand side, we're going to be left with negative 7x. And on the right-hand side, you're going to be left with 2x. This is going to cancel, minus 9x. 2x minus 9x, if we simplify that, that's negative 7x. So you get negative 7x is equal to negative 7x. And you probably see where this is going.
1.
This is already true for any x that you pick. Negative 7 times that x is going to be equal to negative 7 times that x. So we already are going into...
Wait, is the answer 1 or minus 1? Negative 1, I mean. Probably negative 1. Because if we do this... Yes, okay.
Scenario, but you're like, hey, so I don't see 13 equals 13. Well, what if you did something like you divide both sides by negative 7? Negative 7. At this point, what I'm doing is kind of unnecessary. You already understand that negative 7 times some number is always going to be negative 7 times that number. But if we were to do this, we would get x is equal to x. And then we could subtract x from both sides. And then you would get 0 equals 0, which is true.
Okay, but we didn't get x. We weren't able to find x. That's weird. I thought, no, that's definitely a wrong path. But I thought the answer would be 1, but nope.
For any x that you pick, 0 is always going to be equal to 0. So any of these statements are going to be true for any x you pick. So for this equation right over here, we have an infinite number of solutions. Let's think about this one right over here in the middle. So once again, well,
But what does that even mean? Like trying to solve for the equation or like putting the number back in. What does that mean for that? I mean, I'm sure he's going to talk about it still.
let's try to, I'll do.
I will say that I've had teachers who were, I mean, jokingly, but still scared of me because I asked too many questions. Yeah. Like that has been told to my family. Like she asks too many questions and not in a negative way, but still she asks too many questions. I hope I don't ask questions without waiting for solutions, but I do like asking questions. And that was mini me, like child me. I think grown up me has lost some of that spark. I should really get it back.
A little bit different. I'll add this 2x and this negative 9x right over there. So we will get negative 7x plus 3 is equal to negative 7x. So 2x plus 9x is negative 7x plus 2 plus 2. Well, let's add, actually we do that in that green color. Let's do that in that green color. Plus
Okay.
2. That's
I
this
love
2.
that there's a note saying he said green, but he meant yellow.
Now let's add 7x to both sides. Well, if you add 7x to the left-hand side, you're just going to be left with a 3 there. And if you add 7x to the right-hand side, this is going to go away, and you're just going to be left with a 2 there. So all I did is I added 7x. I added 7x to both sides of that equation. And now we got something nonsensical. I don't care what x you pick, how magical that x might be, there's no way that that x is going to make 3 equal to 2. So in this scenario right over here, we have no solutions. There's no x.
I mean, the no solution one is like the most likely of like, okay, this is not a correct equation. But the infinite solution one is like annoying me. Infinite solution means whatever you put the equation remains true. How cool is that? That is really cool. I find that to be really cool.
X in the universe that can satisfy this equation. Now let's try this third scenario. So once again, we'll subtract 3 from.
Like I just realized why. Because you can just remove. Okay, now I feel okay. Because there's a mind game where you tell the person, think of a number and then add to it and then multiply it, and then at the end you're like, take away the number that was in your head, and then you tell them, because you can do the steps with them, and they're like, oh my god, how did you know? This is the same idea. You just remove the like 2 and minus negative 9x just removes it, and 2 equals 2 at any point. I mean, even that, everything is removable, that's why. So I guess that's why. Okay, now my brain works a bit more.
Both sides, just to get rid of this constant term. So we're going to get negative 7x on the left-hand side. And on the right-hand side, we're going to have 2x minus 1. 2x minus 1. And now we can subtract 2x from both sides. To subtract 2x from both sides, you're going to get, so subtracting 2x, you're going to get negative 9x is equal to negative 1. Now you can divide both sides by negative 9. And you are left with x is equal to 1/9. So we're in this scenario right over here. We very explicitly were able to find an x equals 1/9, that satisfies this equation. So this right over here has exactly one solution.
Okay. Cool. Are we going to get a question that tells us how many solutions it has? Probably, yeah. I already see it. Okay.
Solve for x. We have 8 times the quantity 3x plus 10 is equal to 28x minus 14 minus 4x. So like every equation we've done so far, we just want to isolate all of the x's on one side of this equation. But before we do that, we can actually simplify each of these sides. The left-hand side, we can multiply the quantity 3x plus 10 times 8. So we're essentially just distributing the 8. Distributive property right here. So this is the same thing as 8 times 3x, which is 24x, plus 8 times 10, which is 80. is equal to, and over here we have 28x minus 14 minus 4x. So we can combine the 28x and the minus 4x. If you have 28x minus 4x, that is 24x. And then you have the minus 14 right over here. Now the next thing we can do, and it's already looking a little bit suspicious, but just to confirm that it's as suspicious as it looks, let's try to subtract.
We have the 24x on both sides, so we can just remove it.
24x from both sides of this equation. And if we do that, we see that we actually remove the x's from both sides of the equation because we have a 24x there and we have a 24x there. You might say, hey, let's put all the x's on the left-hand side, so let's get rid of this 24x. So you subtract 24x right over there, but you have to do it to the left-hand side as well. And then we're left with, on the left-hand side, these guys cancel out. You're left with just 80 is equal to, these guys cancel out as well, is equal to negative 14. Now this looks very bizarre. It's making a statement that 80 is equal to negative 14, which we know is not true. This does not happen. 80 is never equal to negative 14. They are just inherently unequal. So this equation right here actually has no solution.
Cool.
This has no solution. There is no x value that will make 80 equal to negative 14.
Yes, I do have one note. I noticed that he writes his ends with a line down and then continue. I might be wrong, because this is how I would write an N. I don't know why I noticed that, but I noticed that. Practice time. 4 questions, is this one too many? Like, I would appreciate 3 questions. Oh, you might need a calculator. Well. Let's get ourselves a calculator. I shall be getting myself a calculator. Calculator. And now we have a calculator. Cool. So, why would I need a calculator? Maybe later. We have, I'm gonna probably need to, oh, what did I do? I did something. Can I type? Yes, I can. Okay. So we have the, I'm just gonna distribute this and see where we go from there. We have the negative 5z plus 5, negative 5. Minus 5 equals to negative 2z plus 10. We're going to, I'm gonna cross this there and cross you here, and then let's see where we go from there. We have negative 5z plus 2z equals 10 plus 5. And we have a negative 3z equals 15, and that is solvable. So there is just one solution. Cool. That is the first one. Why do I need a calculator? Oh, you have a calculator. I don't need a calculator. Nice. Huh. Can I show the calculator? Oh, that's cute. I thought I would need my own. Okay, what do I see? I see 25 and 27 do not make up 50, so we cannot just kill the y's already. Remove the y's. But let's try. We have a 23 plus 27, which is 3 and 7. Oh, they do sum up to 50. No, they don't. Wait. They do. Got it. Nice. So we have 50y and a 50y, which means they go away. The answer is infinite, because, and then the 50. Infinitely solutions. Let's try and check it. Nice. And then you, oh, you go to No solutions because we have the 9x on each side, negative 9. Yes, thank you. Thank you. My brain was like 3 plus 7 should not be 10. I don't know why. So yeah, we will be removing the 9x's from both sides, which means we'd get 9 times 6 should be 54. So we would get a 54 equals 108, which is not the case, so there is no solution. Nice. Okay. And then for this one, okay, it's not a no solution. I don't see a infinite solution, so I'm just going to try and solve for the single solution just to be sure. We have the 3x plus 15 equals a negative 4x plus 8. Yes. I'm guessing you don't mean, do you mean this one has one solution? Let's see. I'm gonna move this to the other side and move this to, don't need to solve it. I mean, why not? We have a 7x on this side and a negative 7. Okay. So if we, yeah, the answer is, I guess, negative 1. There is one solution. Nice. That is a loud. This music sounds too Christmassy. Linear equations will always have one solutions if valid. Okay. Creating equations. Why would I create them? I mean, the way I see it, you just create something that you can remove all the sides, and then you get 0 at the end. That would be my no solution creation.
Whereas to use the drop downs to form a linear equation with no solutions.
Oh, cool. Is he using Khan Academy version 10 years ago?
So a no solution linear or equation with no solutions is going to be one where I don't care how you manipulate it, the thing on the left can never be equal to the thing on the right. And so let's see what options they give us. So one, they want us to, we can pick the coefficient on the x term, and then we can pick the constant. So if we made this negative 11x, so now we have a negative 11x on both sides. Here on the left-hand side, we have negative 11x plus 4. If we do something other than 4 here, so if we did, like, say, negative 11x minus 11, then here we're not going to have any solutions. And you're saying, hey, Sal, how did you come up with that? Well, think.
By no solutions, it means the one infinite solution, everything has to be removable. No solution, things just need to be not equal. And that's that.
Think about it right over here. We have a negative 11x here. We have a negative 11x there. If you wanted to solve it algebraically, you could add 11x to both sides and...
Right. Removable x and different constants. Okay.
Both of these terms would cancel out with each other, and all you would be left with is a 4 is equal to a negative 11, which is not possible for any x that you pick. Another way that you think about it is, here we have negative 11 times some number, and we're adding 4 to it. And here we're taking negative 11 times that same number, and we're subtracting 11 from it. So if you take a negative 11 times some number, and on one side you add 4, and on the other side you subtract 11, there's no way. It doesn't matter what.
Yeah, thanks, Abd. I'm just trying to see how it can be rebuilt. How one can make it. Yeah.
X you pick, there's no x for which that is going to be true. But let's check our answer right over here.
Why do I not get a smiley face when I mean, I guess I do get a smiley face. Okay. Okay. I mean, I know what it should be. Just everything be removable from both sides.
Whereas to use the drop down to form a linear equation with infinitely many solutions. So an equation with infinitely many solutions essentially has the same thing on both sides no matter what x you pick. So first, my brain just wants to simplify this left-hand side a little bit, and then think about how I can engineer the right-hand side so it's going to be the same as the left no matter what x I pick. So right over here, if I distribute the 4 over x minus 2, I get 4x minus 8. And then I'm adding x to that. And that's, of course, going to be equal to 5x plus
So our thingy is -8.
blank. And I get to pick what my blank is. And so 4x plus x is 5x. 5x. And, of course, we still have our minus 8. And that's going to be equal to 5x plus blank. So what could we make that blank? So this is true for any x we pick. Well, over here we have 5 times then x minus 8. Well, if we make this a minus 8, or if we subtract 8 here, or if we make this a -8, this is going to be true for any x. So if we make this a -8, this is going to be true for any x you pick. Give me any x, you multiply it by 5 and subtract 8. That's of course going to be that same x multiplied by 5 and subtracting 8. And if you were to try to somehow solve this equation, subtract 5x from both sides, you would get -8 is equal to -8, which is absolutely true for absolutely any x that you pick. So let's go, let me actually fill this in on the exercise. So I want to make it's going to be 5x plus -8.
Nice. And I'm guessing we're going to do the same in this one. Well, similar. Okay. Which of the following have one solution? So this one is infinite. I guess this one looks like a one solution, but I'm not sure. Oh, all that apply. Okay. And this one feels like a non-equal, so I shouldn't pick this. Wait. So at any time, hold up. At any time, we remove the... Okay, here x is not really removable, which is a good thing. These x are all removable. So I'm guessing this is the only right answer because -31 and 31 are not equal. So that's no solution. And yes, and I'm looking at chat, which is what you're saying. And same here, -2 and -31 are also no solution. So this should be the only one solution because we can have x become 4x equals 0, I guess. No, not 0. It becomes 31 plus 31. Okay. Yeah. Nice. And then which one of these have no solution, which means x should be removable. This is 1. But 32 is not. So we take away and it becomes positive 32 equals -32. So that's 1. This one is different. This one here, same. And this one, no. Hopefully. Nice. X can cancel out. Yes. Thank you. And then we have infinite solutions. And that would be everything is removable, meaning cancel out. So first one being the case. Second one being the case. Third one as well. What is happening? Why is everything equal? What is happening? This is scaring me. Everything is equal. It's either that or my eyes are not seeing well. 37x. X by itself. 74. And then 73. Whoa, that was scary. Which one of the following have one solution? So we're just gonna have to remove the ones that are. I guess you are a no solution. You are a no solution. You could be a one solution. And you are a infinite solution. Cool. Nice. Cool. All right, I want to see where we are in the unit because, oh, okay, because Okay, we have this part and then the quiz. 2 videos and then a quiz. Well, a practice session and then a quiz.
So we have an equation. It says ax plus 3x is equal.
Title is linear equations with unknown coefficient. What is, oh, a different thing. Okay.
To bx plus 5. And what I want to do together is to solve for x. And if we solve for x, it's going to be in terms of a, b, and other numbers. So pause the video and see if you can do that. All right, let's do this together. And what I'm going to do is I'm going to try to group all of the x terms. Let's group all the x terms on the left-hand side. So I already have ax and 3x on the left-hand side. Let's get bx onto the left-hand side as well. And I can do that by subtracting bx from both sides. And if I subtract bx from both sides, I'm going...
Okay, we still have ax. We don't know what a and b are.
to get, I am going to get on the right-hand side, I'm going to have or on the left-hand side, on ax plus...
Oh, we're just moving the x's to one side. Okay.
3x minus bx. So I could do that in that color for fun. Minus bx. And that's going to be equal to, well, bx minus bx is just 0, and I have 5. It is equal to 5. And now what I can do is I can factor an x out of this left-hand side of this equation, out of all of the terms. So I can rewrite this as x times, well, ax divided by x is a, 3x divided by x is 3, and then negative bx divided by x is just going to be
negative b.
I could keep writing it in that pink color. And that's all going to be equal to 5. And now to solve for x, I can just divide both sides by the thing that's that x is being multiplied by a plus 3 minus b. So I can divide both sides.
Okay, but like, it still doesn't take away the issue. The issue goes to the other side of the equation.
It's by a plus 3 minus b. A plus 3 minus b. On this side, they cancel out. And I have x is equal to 5 over a plus 3 minus b. And we are done. Let's do one more of these. So another equation. Here we have a, here we have a times the quantity 5 minus x.
I mean, that's quite clear. I could come back to this. Okay, we're just gonna have x be by itself, and that's the goal. Cool. Exercise time. Another 4 question. Okay. So I'd probably, the equation is considered solved when it's in the form of x equals something. Right, yeah. So just make sure x is by itself. It doesn't it's not a social creature. So, we're solving for x, not d. So we're going to have to get d to be okay. So we have the 3d plus xd equals kx and a 9. What we need to do is make sure all the x's are on one side and all the non-x's are on the other side, which would mean hello. Hi. My brain wants to read your name as Lo-Fi, but no, it has to be not like Lofi, maybe? Hi, long time no catch. I mean, it's okay. But I'm glad you're here. So, we're solving for x, by the way. And x doesn't want to be solved. I'm going to move you there, and I'm going to move you here in one go. How cool are my colored pencils? Pencils, pens, whatever. So, I feel like I need to double check. Am I not muted? Because I mute myself sometimes. So we have x, well, dx, not xd. Yeah, because it's a constant. Okay, whatever. Minus kx equals 9 minus 3d. And for this side, we're going to get x out as the common thingy. So it would be x d minus k equals 9 minus 3d. And if we divide both sides by the d minus k, we would get x equals 9 minus 3d over d minus k. And I'm guessing we can remove 1d like that, just one. So we would have a minus 2d. So the final answer would be x is 9 minus 2d over negative k. I can remove... my brain is messing with me. Here's the question I have for chat, and you can choose not to answer. You don't have to answer, but hey. If I say negative 2d plus 9 over negative k, can I have it be positive? Can I remove this and this? Does that make sense? Would it become 2d plus 9 over k? Or am I wrong? I have learned everything about math in... Nice! That's awesome. I also have learned everything, well, most of things in my country during my formative years. And here I am uninforming myself. Wrong. Cool. Okay, so I cannot remove the negatives. But I could... Would that mean even this step is wrong? Because I definitely could move these two around, but since they are... Yeah. How are you? Oh, thank you. It's been a while since I've been here. I missed your lives. Really nice of you. Honestly, I'm good. But if you want a crash course and for me to just like let my brain rest a bit, because I'm sure I'm gonna get this one wrong. I'm mostly good. I had like a few things happen to me over the past 2 months. 2, 3? Wait, how many months? Oh, now it's been like 4 months. Okay. Got it. So the removing of the D is okay, but not the negative thingy. Yeah, I got something called brucellosis, which is not like a serious disease, but it did make me sort of immobile for like a month and a bit. And then yeah. The car accident, I'm happy that everything is fine. But it's not a fun experience to have. So that is my past 3 months. Overall, I'm thankful that things turned out okay. How are you doing? I hope it's not a trauma dump. I'm just like trying to talk about it as lightly as possible. Life happens. 9 minus 2d over negative k. So that's what I need to put here. 9 minus 2d. Uh-oh. I need to do this first. Oh, no, not this one. This first. And then this is negative k. Hopefully. Ah, okay. Not the case. And if we say, let's go back to typing. If we have it be 3D, would that be correct? Ani? No, even that is not correct. Why not? Show a step. No, do not show me a step. here we go, trying to solve it again, even though I know I'm gonna get a bonus question, but that's okay. So we have the, did I not see this negative number? I'm sure I did. Negative 3d plus dx equals kx plus 9. To take, well, I need to move these two around. Oh, 3d would not be negative if I move it to the other side. Is that the mistake I made? We'll see. We have dx minus kx plus 9 plus 3d. Yeah, that was probably the mistake I did. Divide both sides by d? I mean, give me a second. Yes, a lot has happened. Don't multiply. Was I multiplying? Yeah, I'm okay. I have a good support system. Thank you. X d minus k equals same number. So let's just so x would be 9 plus, I think that was the error. I didn't see the negative here. And then we have the d minus k, and then I suppose now I can have the 2d here. 9 plus 2d over negative k. Plus. Oh, I just realized I did not put my phone on Do Not Disturb, which means if any notification had come in, it would have not been a good thing. Alright. Trying again. Oh, come on. Do you not like the way I write negative? Because it is a negative. What's the difference between this one and this one? Same. It's the same thing. Okay. I'm getting angry. Okay, one last try with the 3 and the d here, even though I don't know. Oh really? Oh really? Fine. Thank you. Thank you so much. I'm not happy about it. And then what do we have here? We have a negative cz or z plus 6 and a t and an 83. We can take the z's out from these two, but let's just move the t there so that we have them all together. Bring z to one side and take the z common. That's my plan. That is absolutely my plan. But yeah, I'm just gonna put this somewhere where it's not at the beginning. So 6z minus cz, and then the minus t, and then we have the 83. And we take the z out and have everybody be 6 the number, negative c, negative t, and then we have the 83. So the last answer would be 83 over 6 and a c and a t. 6ct. Let's try. 83 over a 6 and a c and a t. Nice. That worked. Okay. We have a qy and an aq, and then we have a qa and a qy, and then a 67. What is happening? Oh, hi. Divide by Q. I mean, I could. It's just I'm lazy. I want to do the long way. For me, if you remember when I told you, I will take, yay, high school exams. And I hope I get high grades to join the medical university. Thank to Allah, I am now. MashaAllah, that's amazing. Oh yeah. Oh, you did this to yourself. Oh my God. Wow. Oh, Dr. Lofi over there. Wow. Or MD, but still. No. I in my head I thought MD means medical student, but no, it means medical doctor. Wow, that's amazing. Congratulations. I cannot. Oh, well, I mean, I guess I can clap like this, but not with my model. Wow. That's cool. I'm so glad you were able to like bring that dream into life. It's probably going to be 6 years, right? So you have a lot to learn and inshallah a lot of time to do the learning. High school is like a lot of things that sometimes okay, that sometimes feel different, like you feel like you're studying too many different subjects that are not relevant, but like I'm glad you found a way to do well. I'm gonna do the math here because we can take 9 out of 67. And how would that be? Where would we get there? 7 and 2, 58. Okay. So we have a 58y and a... Please tell me. Darn it. Why did I read it as 9? It's Q. This is Q, not 9. I read it as 9. I mean, it's probably not the most fun thing, but... Oh, hi. Hi. I remember reading your name once. Like reading it fully. Okay, I'll try. Argyadi Barat, hopefully. Welcome to the chat. It's been a while. I hope you're doing well. How's life going? I mean, I understand the sentiment of high school sucks, but also it's a learning thingy, learning journey. Whether it has to do with like understanding people or the lessons or like working with a teacher, like everything you will definitely need in your work life. Because like working with an authority, having a group member, all of that you're going to need when you're working. Yay. So I'm just gonna take... Oh, so actually I could have just taken you to that side. No, what am I doing? We are going to take y out, so we still need the qy and the 67y, and then on that side we have the 93 minus qa, so we have the y with the q and the negative 67, and then the 93 and then the qa. All right, so y would be 93 minus qa. Why does this a look like a cinnamon roll? And then q by itself, and then a 67. I'm not gonna minimize, or what is the word? Simplify anything. I'll just post this as is because I don't know if we could do anything about it. 93. Can I memorize this? I'm gonna just write it somewhere. 93 minus qa over hi, hi, Aaron, what's up? Thanks for making it to the making it to the live. Hi, I'm waving my hand. You cannot see that. Okay. The goal is to find y with those q's and a's and everything. So I shouldn't have it be 0, I think. Call me for any health problems. Oh, I have plenty. Do you know about brucellosis? That's the the medical name. There are many common names like Mediterranean fever or Malta fever, depending on where you are from. Took just 6 lectures in every subject. Cool. When you overcomplicate stuff, you become more likely to make mistakes. Agreed. I will still overcomplicate stuff because that's how, yeah, that's who I am. You will not be able to, I'm guessing most of you here know I'm not young enough to be high school aged. I'm in my 30s, so as an old person, I don't think I'm gonna change. Old for you, you know what I mean. Old in your eyes. There we go. Yeah. I can shake my head for the waving of the hand. So we had the 93 and the QA, and then we had the I'm reading it from my note, 67. Let's see if this one is also there. I did not expect to get a correct answer. There's no age limit to learning. That's really kind of you. Thank you. I agree with that. I absolutely agree with that. It's called being a student of life. But you could probably learn more interesting stuff in real life. But this is what I do. This is what I want anyway. AX plus 3x equals bx and a 5. And we're gonna move u here. And that's it. All the x's to one side. So we have the ax and the 3x and the bx, but negative this time. And the 5, 5. That's a 5. And if we take x out as a common thingy, x is like, I'm stretching my leg here. We get the a and the 3 and the b. Haven't taken it yet, but remind me. After 10 years, I'll probably know it. You know what? Not to over. What is the word? Oh God, I forgot the word for when you're talking about yourself in a good light. Anyway, not to toot my own horn, I suppose. My plan is to make a video about brucellosis as a person who had it. It's not my plan. It's what I'm doing right now. But then, I don't know why it's taking me too long to edit. Hey. Oh, yay. Thanks for giving me the answer. Yeah, close. My 3 is in the middle. Your 3 is at the end. Yes, the answer would be x equals 5 over a and the 3 and the b. Thank you for putting it in the chat because I'm going to forget it in a second. A and a 3 and a b. We have a 5 at the top, and then at here we have the a plus 3 minus b. Correct? I think so. And then we get the bonus. We get the bonus question because we got something wrong. Nice. We have. Actually, the Wikipedia page of that disease is, it's a bacteria. The bacteria's name is Brucella, and it's named after a guy named Bruce. I don't know how you. I hope you can't hear outside because I hear too many things. But I remember once saying, "Can you hear what's happening outside?" and then not being able to hear much. When I was editing the video. So I hope you don't hear too much. Is this website using LaTeX? Probably. Should be. I mean, I have no idea. But that would be pretty easier to do. We have a X and a 2. So let's move things around. You go here and you go there. We get a 8x minus px. And everything is negative on that side. Negative r, negative 2. So if we take x out, we get 8 minus p. And then we get negative r minus 2. Answer would be negative r minus 2 over 8 and a p. I'm going to need to put this in the chat for myself. I mean, I write it in the place of chat, but I won't post it because y'all don't need to see that. I mean, and then over 8 minus p. Okay. Because when I remove this, it all goes away. I'm using a program that helps me write on the screen, which is pretty nice. We have negative r minus 2 over 8. That's not 8. Oop. Funny, very funny. Nope, that's not what I wanted. Anyway, negative r minus 2. Removing u. Yes. Huh? What is happening? Oh. Okay. Negative r minus 2. This here tells you what you're doing, by the way. I didn't know that. And then we get the 8 minus p. Thank God. Nice. We leveled up. We went from level 5 to level 6. And now we have a quiz. No, we have a video. And then we have a quiz. And I'm going to be so done. I am so done with learning right now. I love myself how much, how easy I get tired of something. Okay. This is... This video should be like maybe 1 or 2 years old. Should we check? This is why writing on paper is superior. But yeah, but I get the same level of tiredness. Like half an hour, well, depending. Yeah, because this video is from 3 years ago. Got it. Even yesterday, I was doing something that I should have done. And literally 5 minutes later, I was checking the clock. I was like, oh my God, I can watch a movie 2 hours and I don't feel the time passing by. And then I'm doing something I'm supposed to do. 5 minutes later, I'm like, how much time has gone? Anyway, let's watch the video.
Algebra is really the unifying thread of almost all of mathematics. You may think algebra is boring, but it is the one tool you can use to not only understand, but unlock the...
I don't think it's boring, actually. I just think, for the time being, I think it's not easy. And it's a brain-consuming thing.
Universe. Creative algebra is used in computer game design. It powers how artificial intelligence works. Mastering algebra will provide you with the ability to decode and understand many complex systems. In my opinion, if you can master algebra, you can master anything.
I mean, that is the case for a lot of things. If you can master one thing, you can try... I'm guessing that's Khan from Khan Academy, right? I said Khan with a kh, but I know people say k. I don't think actually that's Khan from Khan Academy. No. Because, let me hide my screen again. Me going to the chat screen means I'm hiding my screen away from you. Because his title is what did his title say? Where did his title come in? Here. Head of AI and Chief Innovation Officer. Now you just made me want to go to what? The guy who is doing the lectures is the Khan himself? Wow, that's so cool. I didn't know that. So he's like the teacher as well. Wow. I guess that's him. Yep, that's him. Sal Khan or however people want to say it. That is so cool. Yeah. Oh, his name is Salman. Okay, that makes sense. I'm like, why is it Sal? Yeah, he's the guy making the tutorials. And he made his own website for it. Good for him. I mean, he could have just put it on YouTube. Wow. 2004. Using Yahoo. Yahoo Doodle Images? Sorry. ReadyBot is like chatting again. Chill, guy, chill. Oh, and then it was put on YouTube. But then, okay, so that's a different app. Yes, Wacom tablet. Art Rage. Cool. I have no idea what app I'm using right now. How cool is that? That's awesome. Good for him. Yeah. Teaching is... Dude is also a Muslim, I think. Good for him as well. That's amazing. I mean, I'm not gonna... Yeah. I mean, the from India part is somewhat apparent because I guess I know of him enough to know that. But for the Muslim part, as much as I'm curious, I'm like, good for him. I'm not gonna... Yay! Okay. Wow. Bengali Muslim family. But lives outside. I feel creepy now to look into him too much. Yeah, he was born in the US. Interesting. MBA from Harvard. And MIT. Sheesh. Good for him again. MashaAllah. Okay. Do I need to do the quiz now? I do want to know what app I'm using to draw. Oh, it's called ePointer. That's it. It's called an ePointer. The thing I like about it is that I press something and I then have the ability to write in whatever color on the screen. That was my goal. Is sheesh an old word? Am I old? Yeah, you said that. You said that. You've learned what you are learning in Bengal, and he is Bengali. How cool is that? I actually really like that sense of like national pride you get when you know someone from your region or your country has done something cool. I would like to think I've had a few of those occasions. Or like even history pride. I also have history pride. Yeah. So, we're mathing. We have to. We must. So the Z goes... Oh, I'm not typing. I mean, I'm not... Okay, I don't have the pen. The Z goes to this side. The 6 goes to that side. Let's see where we end up. We have... Hold up. What is happening? How many solutions? It's a different question. Okay. So we have a 9 and a... It's an infinite solution. There we go. Because we have the 9Z and a 7Z, which is 16. So we have 16 minus 6. It's a infinite solution situation. Yay! They do say understanding the question is 50% of the answer already. I should really try to read the question and focus on it. Okay, and let's try to solve for y. So we have a p and a q and a number, and we take all of them aside. We would have a py, a qy, and a 4y. We get an 8 at the end. So in that case, we would get 8 over p, q, and 4. P, Q, thank you, yes. We got there together. We get the 8, and then we get the... Now I'm looking at chat. P, and a Q, and an 8. Nope, not an 8, a 4. Yay. I want to like get the quizzes in one try because I don't want bonus questions. And it's a good threat. It really is a good threat. It's like, if you're not going to do well, I'm going to ask you more questions. Which of those have no solutions? No solutions means everything can be cancelled out. So I see my brain is like singing the epic musical songs that have those words. You know, it's the song from the Prophet. It starts with the word I see. Wow, my brain is everywhere. No solutions. You have a solution. You have a no solution. Oh, okay. No solution means x is cancelled out, but the constant is different. So how many equal x's do we have? Only that one. The end. Nice. And then something else to solve for. Please zoom in. There we go. Thank you. A5, negative 8x, and then bx. We have A5. Well, 5a would... Wait, which one would look better? 5a would look better. How? Huh? Nope. What do you mean? Why? It said no solutions, not infinite solutions. I first understood the question to be infinite solutions, but it wasn't. So yeah, I should read the questions. 5a and an ax equals bx and an 8. We take u that way, we get a, and we take u the other way. Yeah, we get a... 5a, because the number should be written at the beginning. The thing is, when you create variables, number should never be at the beginning. And why am I thinking of that? Yes. Ax minus bx equals negative 5a and an 8. We take the x out, and when we have the a and b, and then x would be negative 5a minus 8 over a minus b. Someone write this in the chat for me. Because I'm not going to memorize this. I'm going to write it myself. It's okay. 5a minus 8 over a minus b. Cool. And here it is in the chat. And we have negative 5a minus 8. Oh, that's not a minus. What did I do? Minus 8 over a minus b. And then we check. What did I do? What did I do? Did I get some sort of a... something... Yeah. We got a bonus question. Trying again. A5. Well, 5A. 5A. And AX equals BX and an 8. So, we have the negative 8, and then we get the negative 5A. So that is still there. On this side, we have X. Oh my god! It's negative A and negative B. Look, I didn't see this negative. Then it becomes negative A and negative B. Okay. Hopefully that is the answer. You are negative. Everything is negative. And if you tell me to simplify. There we go. So help me God. How many does you this have? Cancel out. Huh? Yeah, A minus B wasn't right. You're right. Yeah, it was negative A. Thank you, Aaron. Yeah. And now my brain is telling me, is it Aaron or... I mean, like, I would normally say Harun, but that's a different name. Yes, Aaron, I think. That should be the correct pronunciation. 3 times 14 would be... 14 and 14 is 28. And another 14 to... 42? Really? Hold up. 14 and a 3. 3 times 4. 50. No, it is 42. Okay, it is 42. Nice. So the answer is no solution, because what we would get is we would get a 14z plus 42 and a 14z plus 21, which means the answer we would get is 42 equals 21, which is a no solution. And then we're probably going to get our bonus question. Oh, no bonus question. But I'm guessing... Okay, we did not get demoted. That's a good thing. Everything is still purple. I am not going to start lesson 5. What do you... My brain is fried already. Look at the cute blocks. Multi-step inequalities. I don't like inequalities. I call for world peace, you know. We have a lot left. I did get 80%. And it's like, redo this, please. I'm like, no. Yeah. Unit test? Okay. I mean, that's in like, if I finish this by the end of the week, I should be probably, maybe next week. We'll see. Yeah. We did, this is unit 2. So if I go to Algebra 1, unit 1 is all finished. Unit 2 is like, what is the percentage? We will see a percentage somewhere. No, not here. Like if I click unit 2, it will tell me we're 58%. Yeah, it looked like a... In vector, we were taught that tan 90 degree is 1 over 0. What? What is that? That's why you need to solve for inequality. Really? If we solve for inequality, we'll get world peace? You know what? That's a cute cat. If... Hold up, let me use my brain. If me doing math solved equality, like world peace and all of that, I would do math 24 hours a day. That's me saying I will do something that makes me rather uncomfortable. Yeah. Like me solving math on stream is not a comfortable thing, but it is something I've gotten myself used to. Being like not the one who knows everything. That makes me rather uncomfortable. So what should we do next? Because my brain is fried. I mean, I know what I'm going to do next, but I'm still going to put it not for a vote, but for like open for suggestions, because I do want to finish the video that we started yesterday. I remember being at minute 8. Let me open it first. Okay, close enough. I remember being at minute 8. And YouTube has saved it as 7 minutes and 30 seconds, which is close enough. If anyone else has any suggestions, we could either... They don't give enough exercise. We once had 200 questions in one unit. I mean, that's enough though, right? I'm guessing you don't mean in an exam. Like, if a section has a lot of questions, means you get a lot of practice, and that's a good thing. So yeah, if anyone has suggestions for, I guess, later, you can you can put it on Discord, but then the chance of me being able to watch it on stream is not always 100%. That's a good idea. That's a really good idea. I mean, I will say, okay, that was a pretty good stretch. Oh, you guys should do the same. The stretch I like is like hand on top of head, palm facing, well, you have to interlock your hands first, and then palm facing up, and then pulling. So that's what I would do. And then when you get your hands down, you do it like arch. And then I also like the one where you honestly, for the posture, I do believe mine is currently okay. Like I said, I put the mic differently, where hi Asher. I put the mic up higher than usual, and I have to sit with a straight back, which is annoying me, and that's a good posture. Normally I would sit like a gremlin, but not today. I'm sorry. I apologize for having good posture today. Yeah. But again, you guys should also do a posture check and a stretch, because you know, when you, like, I personally sometimes do that when you have your phone in hand. I'm hoping even if you have a phone in hand, try not to have your neck be too low. I always check that for kids. I'm like, at least have your head held a bit higher instead of like looking down. I think that would hurt your neck and shoulders, right? Yeah. Okay. Thank you for all of the nice checks. And now we look at this video that I'm 8 minutes in, but anyone who was not here before, I could give a summary. I don't think I would give a good summary, but like, it's a paper presentation. The paper's name is Pre-training under infinite compute, meaning how would you pre-train a model, creating a base model, if you had limited data but a lot of GPUs and computers at your disposal. So they're discussing that. Yes. And I'm going to play the video. We're going to check for sound, if it's good or not good. I think it's reasonable, actually. They don't have excellent audio, but it's not that bad. It's pretty good.
In this talk, we revisit this classical question of data efficiency, which has been studied in many times in the past, but really take it to its limit and consider what would you really do if you had infinite compute. And we also get to revisit this with a fresh perspective from the last few years of the success of scaling loss, being able to estimate loss as a smooth function of compute and the amount of data that you have. So we really consider this question of data efficiency from first principles to think about what is the best possible loss that you can achieve. And we really build out the scaling loss to measure this. In terms of a brief summary of our results, we first find that current approaches overfit, and current approaches such as scaling parameter count and scaling
Actually, that's a good question. I wouldn't call... Yes. Thank you, Coffee, for the answer. So the point is, yes, the internet data being one thing, but as they mentioned in one of the previous slides, if we, I feel like I'm presenting. If we go back a few slides, there are some data things that you would want a dedicated model to, like even if it's like your company's data. Obviously, having a base model is always necessary, but if the base model... I don't know if it's a good thing to have your base model only trained on your data. Do not ask me that. But still, let's say you want a model that is only trained on medical data, and that's definitely very limited and does not equal internet data level. Even then, internet data is not always infinite, you know? Like, we have maybe petabytes. I don't know how big it is, but we have a lot of data. And if you have a model that is trained on everything on the internet as of today, a week later, you now have more data, but it's like the addition. And I'm guessing they want to be able to even enter that addition of data. Anyway, my brain is all over the place. Yes, even the training a model on any language that is not as everywhere as English. Because there are languages that have small number of speakers or small number of users, or even, like languages that have a big number of speakers and big number of internet users are lucky ones. But I feel there are a few websites that tell you how many languages there are. Some of them say like 5,000. Yeah, so all of that is very limited data. I think in this case, we're not really talking about internet data. Rare languages or low resource languages have people that care about it, but don't always have the same amount of resources. And compute being one of them. But hey, today we're thinking we have infinite compute.
In terms of a brief summary of our results, we first find that current approaches overfit, and current approaches such as scaling parameter count and scaling epochs and whatever, they really cannot leverage more compute, even if the approaches had more compute available to them. So this overfitting prevents you from leveraging infinite compute, even if you had it, which is kind of an undesirable property. On the other hand, in this talk, we're going to design scaling recipes based on classic algorithms that monotonically decrease the loss as a function of compute. So this gives us both a monotonic decrease, so we can actually leverage more compute if we had it. And the second interesting property is that we're going to achieve this clean power law scaling. And this power law scaling allows us to estimate the performance of our algorithms with different compute budgets. But more interesting, allows us to estimate the best possible performance of our algorithm under infinite compute by taking the asymptote of the scaling law. The asymptote of the scaling law tells you what is the best possible performance if your algorithm truly was given as much compute as it wanted. And we believe that this general tool of asymptotes allows us to make really strong predictions about what algorithms are going to be useful in the future. As a brief overview of our talk, we're going to start.
Oh wow, we're still at the overview point. One thing, I didn't pause for any ads today, I just realized. So sorry about that. Yeah, infinite compute is like theoretical, but also a way to ask what if we had fixed amount of data that we really wanted to get the most out of? Yeah. Yep.
Start off by talking about the baselines that we're going to consider in this work and how current approaches operate. And then we're going to really enter this infinite compute utopia and think about, if we really had a lot of compute, what are the best possible recipes that we can do? Here, there's going to be a lot of
See, they're even calling it a utopia.
asymptotes to really estimate the best possible performance and compare different algorithms, showing that algorithms do really matter in this finite data regime. Finally, we're going to take it back and think more about like the practicality of our interventions. Are these things that actually make sense? At what scale do they make sense? Do they continue to matter for like downstream tasks? And we're really going to take it more carefully and see if this makes sense. I think here is a good time to pause. Are there any questions about what we've discussed so far, what we're planning on talking about today?
No. Go ahead.
I guess my question is more on sort of, is this a theoretical exercise or is it like something more practical? Whereas like my understanding is that currently, available token counts are far greater than parameter counts. And so we're not really in an overfitting regime, but maybe.
Yeah, that's a good question. So I think the perspective we're going to take in this talk is that even though right now we are not data constrained, around 5 years from now or something, then we are going to have a lot more compute than data. And then all of these interventions are going to start making sense. So this is going to be a very thoroughly empirical paper in that we're going to be doing a lot of experiments to try to guess at what you would want to do. But the end goal is to make predictions about what you would want to do in a data constrained future, which might not be where we currently are at right now. In terms of the relationship with theory, a lot of our scaling analyses and like algorithms that we try do come from theoretical inspiration because theory does usually consider asymptotics of what happens when compute or data goes to infinity. So this will provide a lot of inspiration for the algorithms, but the actual methodology will be quite empirical. Does this make sense?
Yeah, cool.
Mm-hmm. Yeah, any other questions at this point?
No.
Okay, great. Then we can get into some experiments. Before we do that, let's first get into the empirical setting that we're going to be using in this paper. So to simulate a data constrained future, as mentioned, we don't have enough compute to saturate the 500 trillion tokens of text on the internet. So instead, what we're going to do is we're going to limit our algorithms to a small number of pre-training tokens. In this talk, it'll be 200 million for most of the talk, but I think by the end, in section 7, we're really going to ablate whether these things are, like whether they generalize or not. In terms of the actual pre-training recipe we use an optimized pre-training recipe. So this is things like using transformer, using an Atom W optimizer. And this pre-training recipe is borrowed from Marin, which is this wonderful pre-training framework that we and a couple of others at Stanford have used to pre-train a model that's stronger than Llama 8B. So we know that we're like faithfully representing practice in terms of what works for language model pre-training.
Good question. I'm not actively trying for a PhD. I applied for a program 2 years ago. Was it 2 years ago? Well, it was 2023, end of 2023. Yeah, exactly 2 years ago. And the program didn't even open. So I would like to think that it was not rejected, but they didn't open the program. And it is something that I would like to do at a point. And I do think that if I apply, well, I know I don't have the time for it now. That is for sure. I have a full-time job. But there are a few other things that I'm doing that limit my time. One of them being I'm actually taking a paid course that is like a full, is it a full year thingy? It's a long thingy. Anyway, so that is hopefully helping me be on track. And I have not applied for anything, not recently, but I want to feel ready when I want to apply. And I do believe that my math is low, and even like my math would help my machine learning skills. That is my goal. Yeah. And I would probably apply for something that has to do with computer science and machine learning. Yeah. So, but I have not applied for anything. It's just something like at the back of my mind. And me like doing those streams, it is in my mind all connected to that. Like that is the goal I'm going for. But like even the PhD itself is not really the goal. The goal is like being informed and continuously learning. Oh no. I mean, I have a master's, so my PhD would be either 3 or 4 years, depending on the program. Or if I do part-time, it would be like at least 6 years. But I know in the places like the United States, their programs are master's plus PhD, so it's always like 7-year thing. Yeah, master's was 2 year for me. Some people do a 1-year master's, which is like a 365 day thingy. I know that there are a few programs in Britain that help with that. Yeah. But I'm probably looking for something that's like 3 years because I want to be done as soon as possible. But even then, it's I guess your supervisor decides when you're done. Or maybe yourself. But like even there are different types of programs. There are research-based ones. There are not really teaching-based ones, but like ones where you have to teach. Otherwise you can't pass. Yeah. There is a thing called McPhil, which is not PhD. There is a thing called like some sort of advanced degree that is only is that the McPhil? That's only research, but again, it's not equivalent to a PhD. So if you want to teach at a university later in life, that would be yeah. Ooh. Oops. See, there was an ad. Oops. Ad break. Sorry. I mean, I could encourage you to go to YouTube when there's an ad break. I don't know if it helps. Yeah. But yeah. I don't know how many of that I answered, but yet there is an ad break. I can drink some water while that is happening. I think the community is back now. So, did I answer your question? I think I answered your question. Let me know if the answer was satisfactory. Yeah, PhD has to do with a lot of research. Some course taking, like maybe the first semester or the first year you take some courses, but it's mostly you research something. And then even like it's called like making a contribution to science, meaning you have to do something that no one has done, which is scary. At least master's level, you can replicate what other people have done, but PhD level, you have to make a contribution to science, a new contribution to science. Yeah, even if it's like as small as possible, still.
Since we are assuming infinite compute, we think that the standard regime of chinchilla scaling and this inference compute overtraining is kind of not what we're interested in. We're really like, if we know that training larger models is going to help us, we're going to train these larger models to get more data efficiency. So in this setting, we're going to be training models that are much larger than what people currently train. So 30 times larger than chinchilla, 3,000 times larger than standard overtraining practice. But hopefully it reflects that in a data constrained future, we are also willing to train much larger models. In terms of the metric that we use, we are going to be sticking, for most of this talk, we're going to be using validation loss. We find that validation loss, many people have found previously, that validation loss is a great proxy for.
Are all paper PhD level contributions? Honestly, that is something I'm unclear on. No. I don't think so. Like say this work is PhD level? Like one of... Oh, probably. That one looks like a PhD. I mean, according... But it will take more time. PhD? What do you mean it will take more time? I mean, if it's a... I'm sure it depends on the country, but I know some universities allow you to stay if you're saying I'm not done. Like you are the one who decides if you're done. I know people who have stayed at a PhD for 8 years, but I know of people. There are universities that it's like, okay, you have a 3-year time with us, finish by your deadline, or you have to pay more, which, yeah, I guess a lot of universities do that. Yeah. To answer your Coffee's question, like, I know one type of paper that every PhD students write is it called a summary paper, where you say this is what's happening in the field. So that's not like, or one of them could be like, this is the data I collected, and here's me analyzing the data, and this is the algorithm I don't know how many papers you can get out of a PhD, maybe 2 or 3. But like, I know one of the papers have to be like, this is my finding, but that's about it. Right? I wish you luck. Thank you. Hopefully one day you'll get a PhD. I mean, I hope so as well, but even now I'm worried, like, how depressed will I be when I'm a PhD student? Like, even though I love learning, I know I'm not always happy when I'm doing it actively. Because I'm like, oh, I wish I could just enjoy life. But then when I'm in, and I do want to enjoy life, but then I'm like, I'm not learning. I need to be learning. Yeah. It's a funny relationship I have with learning, and like when I'm doing something that I call unproductive, then you're like, oh my God, why am I only doing that? But then when you do something productive, you're bored out of my mind. I'm bored out of my mind. Anyway, yeah. I think, again, this is me using streaming as a way to help myself get over that, like, would I sit for an hour and do math practice if I was not streaming? I don't think so, you know? So you guys are like absolutely helping me do more learning. So I'm really thankful for that. And I hope I'm not wasting you guys' time, you know? Yeah. Inshallah. I don't think this year. I really don't think next year, because I already have plans, work related, obviously. But yeah. In my mind, I'm like, at least be in a program before you're 35, because I will just have less energy. What? Usually at least 5 hours of math is needed every day. Good. Well, not for me. Maybe for you. I'm guessing you mean as a student, so that you can have it like be fluent in it, right? I'm gonna play the video and mute myself and take a tablet thingy, so my face might stop tracking me for a second. So see you on the other side.
The capabilities of a model, especially in downstream tasks and for controlled algorithm changes. We also confirm ourselves later in this talk that this actually does lead to downstream accuracy benefits. So we're going to stick with validation loss for now. And finally, we're not going to allow for any human supervision. It's a common practice these days to basically incorporate a lot of external supervision to train better models, such as prompting models to generate synthetic data, using external reward functions or external data or distillation. These are things that we're not going to allow ourselves to do, because we are mostly interested in this pure question of what is the most value we can extract from the data, even though these are things that might help. Hopefully, these are things that stack on top of what maximum value we can extract from the data in the first place. Yeah, please ask any questions about the setting.
Extracting maximal value from data, but without overfitting. Yeah, I guess you have to practice anything that you want to be good at. And now I'm thinking, but if you practice every day, like, for example, exercising, then you don't have time to recover. Would that be the same for brain exercises? I don't know.
Okay, if not, then we can start jumping into experiments. So the first thing that we're going to do is we're going to characterize maybe people's gut reaction to how well do existing methods handle data constraints. So I think there's two main ways in which language modeling people, at least in the open, have really considered this in the last few years. One is that if you have a lot more compute that you're willing to spend and you have a limited amount of data, one thing you can do is you can repeat the data. This is like a pretty classical, like epoching the data is a pretty classical thing that people have been doing for a long time. But there's been recent work, like in the last 2 years ago, there's been work showing how it helps pre-training. There's also another reaction, which is that if you're bottlenecked by the amount of data, you can continue to train larger and larger models because larger models happen to have a better inductive bias and learn better from a finite amount of data. So we're going to characterize the performance of both of these recipes in our data constrained regime. The first thing that we try is epoching the data. In this plot, we're training our 300 million parameter models on 200 million tokens. And on the x-axis, we vary the total epoch count of training. Each of these points is a separate pre-training run. What we notice is that as we epoch the data, we actually get a performance improvement. And it looks like 8 epochs is better than epoching the data once. But it does not go forever. And if you...
Oh, wow. I guess I'll try to say what epochs mean just because he keeps saying epochs. Like you iterate. Well, it's not really exact iteration, but you iterate on the same amount of data for training with different weights. Like your weights have to change in each iteration. Yeah. Parameters and weights probably change. Like learning rate probably stays the same. Well, it does change here. It's written down here. But yeah. So you're iterating on the same data with different weights. Does that make any sense?
You continue to try to epoch the data more and more, your loss starts going up. At each of these points, for each epoch count, we also tune the learning rate just to make sure we're getting the...
But like 100 epochs is just actually reasonable. I was about to say too much. No, it's not.
Maximum value out of these pre-training runs. So epoching...
Yeah. Weights continuously change. But isn't it like from epoch to epoch? How many iterations do we normally do? No, weights are changing. But in one epoch, I don't think one weights would change, right? Because that's how the iteration would work. Am I wrong? Maybe. Okay. I could be thinking mini batch updates.
As perhaps expected, eventually overfits, and it's not some operation that you can do forever. The next recipe that we try is we try increasing the parameter count. So now at each x value, we are trying a different parameter count. And for each parameter count, we are jointly...
They aren't... They aren't doing epoch updates in this. That's for a very small amount of data. Okay. But here we're not really talking about parameter count. Here we are talking about parameter count. So and the epoch count is 8, 8, 4, and 4. Only 4 epochs.
Tuning the learning rate and the epoch count in an attempt to get the best possible loss for this fixed parameter count. So we try this for 150M, 300M, 600M, 1.4B. What we find is there's very strong diminishing returns to increasing the model size. And even at the end of the spectrum, we're actually observing this overfitting in which the larger models are actually, this largest model is actually performing worse than the 600M model.
But is it by a lot? Like, yes, it is ticking up. Like, okay.
model. So one conclusion that one might draw from this, that one may incorrectly draw from this, is that this point over here,
Is
this
the
600
optimal?
million parameter model trained for 200 million tokens, is the best possible performance under infinite compute. Now, if you are following these recipes, this may as well be the best possible loss that you can get. Interestingly,
Yeah, it's not by a lot, but yes. Even if it's 0.01, it's still like, okay, it's worse. So yes, it is undesirable.
in this infinite compute regime, the actual algorithm that you use to train on the data matters a lot more. And this is kind of what we're going to cover for the rest of this talk.
Okay. Next slide, please.
Cool. The next recipe that we're going to consider is the natural reaction of that if we are training.
That's fair. You pay twice as much for a car. You don't want it to be worse. Yeah. That is like 1.4 versus 600. True. That would need a lot more compute.
All of these over-parameterized and epoch models, perhaps it's necessary to regularize the pre-training to get the maximum value out of the data, out of this data, especially since these models are so much larger and epoch so many more times than standard practice. The first thing that we do is for each parameter count, we jointly tune the learning rate, epoch count, and weight decay. We aim to be thorough about this. So what we do is for any hyperparameters that we display, that we find locally optimal hyperparameters. What that means is that these hyperparameters of 3, -3, 16, and 0.8 for the 150 million parameter model, if you incremented or decremented the learning rate, incremented or decremented the epoch count, or the same for the weight decay, all of those 6 neighbors perform worse than this choice of hyperparameter. So this indicates that this is really like our best attempt at the best possible loss for this parameter count. When we tune these hyperparameters, we made us a pretty finding that kind of went against our knowledge, which is that the largest models, the over-parameterized models especially, benefited from a weight decay that's much, much larger than standard practice. So usually when people pre-train language models, they'll use a weight decay of 0.1, most likely cargo cultured from the original GPT-3 paper. But what we find is that when we're tuning these models, especially for these over-parameterized models, the optimal weight decay is over 30 times higher than the standard practice. And it's really important to use weight decays that are like 3.2, which is much higher than what people normally do.
Wow.
After we tune these hyperparameters, we find a pretty large loss improvement over the standard recipe. So this red recipe over here is a standard parameter scaling epoch recipe that we had seen in the previous section. Now what we're going to do is, in addition to tuning the learning rate and epoch count, instead of fixing the weight decay to be 0.1, we're also going to tune the weight decay in tandem with these and find that it makes a huge gap, especially for our largest models. Though this is the first exciting thing that we're getting this much higher performance, the second nice thing that we find is that the loss actually follows a clean power law. So we find that for our 4 points, we're able to fit this power law that kind of reasonably interpolates the data. So this power law has a couple of interesting properties when we fit it. The first interesting property about this power law is that if you look at the model scaling exponent, or how fast the loss drops as a function of the parameter count, we find that the exponent is close to 1. This is pretty different than the data unconstrained regime, which is studied by chinchilla scaling, where people in practice usually find exponents that are much, much smaller than 1. So for example, the chinchilla model scaling exponent is 0.34. This indicates that in the data constrained regime, you're getting a much faster improvement from increasing the model size. Perhaps what's most interesting.
I mean, I am quiet and letting him talk because I'm trying to understand what he's saying, but I also feel guilty for not saying anything. But I'm curious if we will have a slide on evaluation. Maybe. We'll see. I'll just let him talk because he's the one doing the thing.
Thing about this is that we actually don't care about this exponent. In this truly infinite compute regime, though this exponent is nice to saturate the performance, what we actually care about is the limit as the parameter count goes to infinity, because we're willing to train as large models as possible. So what we find is that the actual loss that we find, the actual asymptote of this power law, 3.43, is something that captures our best estimate of the best possible loss under infinite compute. I see some questions in the chat, so perhaps I'll answer them. Oh yes, so for the data set for this paper, we are using DCLM as the pre-training corpus. Thanks for clarifying. For all these initial set of experiments, we're going to be using 200 million tokens. And in a later section of this talk, we're going to be seeing how these performance gains change as you change the amount of data to seed tokens given.
Okay. So they argue that log loss is a proxy for model performance, but do validate that on some results. I think it was a few benchmarks. They did talk about some benchmarks in the beginning, didn't they? Like before yesterday's viewing?
How do you trade off between larger model with higher regularization versus just smaller model, or MOE, where active parameter counts are less? So over here, what we are finding is that if you correctly tune the regularization, which again is not something that actually costs you compute, it's always better to train these larger models. So it's more a function of how big are you willing to train a model that determines how big of a model you want to train. This regularization you should tune per parameter count, and you'll always get an improvement from doing that. In terms of the relationship with MOE, yeah, I think the MOE has like a pretty interesting relationship in terms of like the parameter count and inference time. I think for now, we're really not going to think too much about the parameter count and inference time, and perhaps we'll revisit this as a later point about like how many, like which methods make sense if you care about inference parameter count rather than train parameter count. For now, think of the parameter count as just a proxy for how much compute we're spending, and we're using this to build the clean scaling laws.
Okay.
Any other questions? If not, I think the main takeaway is that we're really excited by the tool of asymptotes. If you correctly tune these hyperparameters and correctly think about how to train these models, we find these nice monotonic relationships, which actually allow us to very cleanly predict how loss is going to change as a function of compute. And this really allows us to estimate the best possible loss under infinite compute, which is the regime we're going to operate in until we care about like the practicalities of these methods.
And
Cool.
ooh,
For this next part, what we're going to discuss is we're going to discuss an alternative scaling recipe that spends compute in a different way than parameter scaling does. So even though parameter scaling is one way to spend compute, it's not the only possible way to spend more and more compute to train better models. A technique that worked really well in classical literature is ensembling. So instead of training a 5x bigger model, what we're going to do is we're going to train 5 models of the same size. So not increasing the model size yet, but just training multiple copies. And each of these models is going to be given a different data order and a different initialization, but is otherwise the exact same training procedure. After we train these models, we're going to take them and we're going to average their logits at inference time. So this is the simplest way to aggregate these models after we've trained them completely separately from each other.
Mm-hmm.
So this is one way in which we can spend more compute. A finding that we found really, really surprising is that instead of training these bigger models, instead of training these around 5x bigger models, we find that it's actually better to train multiple copies of the same model, even when matching the total parameter count. So in this plot, the purple curve over here corresponds to something you're familiar with. It's the parameter scaling as you tune regularization correctly, which follow the power law. In addition, what we do is we take these 300 million parameter models, we follow the exact same training recipe and just train multiple copies of them. Each of these points corresponds to a 1 ensemble, 2 ensemble, 3 ensemble of all like 400 million parameter models. And we're matching the total parameter count of the ensembles, since this kind of corresponds to how much they cost at inference time.
So it's like training one model, everything being the same, versus training multiple models? The ensemble ones? Or is it smaller? Because it's like training multiple models and then averaging that out versus one. Obviously, the ensemble would win. Those things look similar.
Under these scaling laws, we find a pretty surprising finding that instead of training larger models, which is maybe perhaps the de facto paradigm.
So they take this number of parameters, I would say, and then take it from there using ensemble. And these are bigger models. Okay, got it. Ensembles like groups of people working together rather than one superbrain. Exactly. Yes. Same as musical ensembles. I know the word for musicals, but yes. I understand what it means in a machine learning context.
In language modeling.
I'm just checking, like, is it the same amount of data or like the scale? But purple is model scale, but cyan, I suppose, green, is like taking this instant and then doing ensemble with different levels.
It's actually better to train multiple copies of these models and aggregate them after the fact. What's extra nice is that increasing the ensemble member count follows a real...
Wouldn't it like be worse for overfitting though? Because you're copying the same thing. I mean, they probably did that though. Remember they have infinite compute? Yes. I mean, I forgot, but yes.
Really clean scaling law. So what this corresponds to is that if you increase the total number of ensemble members, this also decays at a rate of exponent 1. And this has an even lower asymptote of 3.34. There's a question about, did you track gradient norms during pre-training, and how did the gradient explosion near the end phenomenon behave with your...
Oh, I love that the answer may surprise you. Ooh, okay, they're going to bring up overfitting. Okay, looking forward to that.
...chosen weight decay. Do you know if it got better or worse?
Oh, what was the question?
There's a question about, did you track gradient norms during pre-training, and how did the gradient explosion near the end phenomenon behave with your chosen weight decay? Do you know if it got better or worse? Great question. We didn't track the gradient norms, so we have them, and you're free to look at our weights and bias logs. We've open sourced all of this, so feel free to look at it. I don't remember the gradient norms. In terms of the gradient explosion, I guess we've seen this phenomenon with this high weight decay pre-training, which I guess is corroborated by prior work, which is that when you train with high weight decay, your loss improvement is slower at the start of training and then becomes very rapid at the end of training, which I think is perhaps related to the gradient norm explosion. We didn't track too much about the fine-grained details about what happened, but we did find that it was better terminal loss to have high weight decay, so we stuck with it. Yeah, good question. So cool. What's really encouraging about this is now ensembling is a recipe that also has clean scaling, but it has a lower asymptote. And this lower asymptote kicks in at like pretty low parameter count, or not like relatively like reasonable parameter count, such that we can actually observe the crossover, which kind of tells us that we're going to be fine. Yes, so there's a question about what the ensemble structure is. We're using the most vanilla form of ensembling, which means that we have multiple copies of the model, all trained completely independent of each other. And then after the fact, at inference time, we're going to average their like logits. So there's no MOE structure to it. Maybe perhaps an experiment of interest is that we had tried training these models jointly. So right now we're ensembling. One really important component.
Hello, Tech AI, and then PJ4OM. Hi, hello, welcome to the chat.
Is that we trained each model independent of each other. If we try training these...
So they're just take a vote on the prediction, averaging it. Yeah, averaging the logits. Cool. Yeah, I mean, to put it metaphorically, yes. Group brain is also always going to have a better average than a single person. Yeah, so that makes sense. Yeah.
These models jointly together, so constructing a structure which is 5 models held.
So in the infinite compute part, it would make sense to go for that.
Together, that where their logits are averaged at training time, not only at inference time, we find that this type of model barely offers any improvement over a single model, suggesting that the reason that ensembling is helping is not about sparsity, but it's more about the random training trajectories that are happening.
What does that mean?
So to give some additional intuition for why we think ensembling is helping, it's obviously hard to tell the exact explanation for why ensembling is helping. But perhaps our core intuition comes from this prior theory paper from this wonderful theory paper by Zeyuan and Yuanji. And what they suggest is that data often has this multi-view property, which suggests that training examples, there are many possible features that correctly classify a variety of training examples. To best fit all of the training examples and generalize to the test set, it's best to use all of these features. However, single models, no matter how large, have this bias towards learning only one of the possible features, only a couple of these features that correctly classifies the majority of the data set and then leverage.
And I have a question here. how would we know all of the independently trained models for the ensemble all don't pick that one feature that they're biased towards?
Memorization to remember like the rest of the data set. Under this view, ensembling is quite nice because the randomness that you get from independent training trajectories is allowing you to learn the whole set of features.
Yeah, each model learns its own way to solve the problem, optimize the loss. Yeah, and I guess the randomization does help to have them not be on the same path.
Though each individual training trajectory is not going to learn all of the features. And this is why we suspect that just making the models more sparse isn't what's going to solve this. What you really do need the independence property to get them.
They might though. Okay, that would be unlucky, or yeah, less probable.
Major benefits of learning all of the different features. One experiment that we conduct in this direction is that for each ensemble member, earlier, we have seen this black line, which shows the loss as a function of the number of ensemble members that we have. So this was the scaling law that we saw earlier, but it was also each ensemble member was trained with the exact same hyperparameters as the best hyperparameters for a single model, or k equals 1. What we actually care about is the asymptote as the number of ensemble members goes to infinity. So what we study is whether the optimal hyperparameters remain the same as you send ensemble count to infinity. So for 12 different epoch and weight decay pairs, we try fitting these scaling laws by training 5 ensembles. What you find when you take these limits is that under the limit of infinite compute, first of all, at finite values of k, the actual ranking between the hyperparameters changes, and under the limit of infinite compute, the best hyperparameters for an ensemble correspond to each member being trained with less weight decay and more epochs.
We see it here, like, can I remove the CC? Here. The orange one is, or pink one, is going lower, and there are more epochs, and the weight decay being smaller.
Intuitively, this is suggesting that you want each model to overfit to the training data in its own.
Oh darn, I did not look at chat. Hi, welcome back. Sorry about that. I am not monitoring Twitch. All right. Huh. All right. We have a few seconds, but yeah, I guess chat is back. So more epochs, less weight decay here.
Own unique way to learn its features maximally, and you don't care about the memorization as much because you're going to be able to ensemble over a diverse collection of models that you get from the randomness of initialization and data order. So this allows you to actually, you find that it's actually best to pre-train these ensembles by using more, well, like hyperparameters that encourage more overfitting than standard pre-training.
For ensembles, it's okay to focus on one thing because everybody will focus on different things, and then we get, hopefully, the best answer.
So this concludes our ensembling recipe, which kind of gives you a better way to pre-train under this infinite compute limit. I think at this point, I'm going to hand it over to Konwoo.
Hello. Okay, so authors kind of introduced like the main scaling recipes we use in this paper, which to recap, we have sort of the current standard recipes people use. Then we have our regularized recipe where we really crank up weight decay. And then we have sort of vanilla ensembling where for a fixed parameter like
I will say they're doing too much for one paper. I mean, it's a Stanford paper, so I understand that, but they're doing way too much. Like, that's awesome.
For the individual numbers, we can ensemble multiple numbers together. And so in this section, we're going to look at how far can we push our performance if we sort of compose all of these like data efficient interventions that we've introduced so far, and how much better is this compared to the current practice. And
I'm gonna need to see how much longer will they be talking, because Ooh, yeah, no, I definitely need to go in 5 minutes. And there is more than 5 minutes left. Okay, well, we'll see. A lot. They've done a lot.
So sort of the main interventions that we've introduced allow us to sort of scale compute along multiple axes now. So we have scaling along sort of the parameter axis, but now we also have scaling along the ensemble like member axis. And so what we can now do is we can sort of compose these two.
It is a long video, agreed. I guess, I don't know. It's a online presentation, but is it like a, because normally paper presentations are not hour long. So the fact that this is a live hour-long thing is pretty cool. It does say seminar, which means they were probably invited to talk for an hour instead of it being a conference. Conference paper presentations are not that long. Even if it's like a big, even if it's actually some of them are though. Stage thingies are quite long. Stage presentations can go from half an hour to 1 hour, but like workshop ones are max 15 to 20 minutes.
Scaling axes to characterize the best possible performance, like under infinite compute, under this double limit.
I mean, I suppose it's not ideal for those here for math class, but I think we have it very separated, right? We're like here going to the video. I hope nobody feels like a hostage when watching my content. You are free to watch whenever you feel like it. Still, it's interesting. I won't be able to finish it, but I might watch it at my own time or next stream. Next stream is going to be a short one because it's going to be a weekday stream.
As we send both of these quantities to infinity. So concretely, what this limit looks like is it's a limit over two parameters, which are n and k. And n here corresponds to the number of parameters in each ensemble member, while k corresponds.
Here's something for the math class people. Whenever I see something written out, like I don't think I guess the correct word would be an equation, but it scares me so much. Like, thankfully they have some of these written down. D is number of tokens, N is parameters, K is ensemble members. Why choose such limits? Hey, see, it made you happy and it made me like, ooh. Why isn't D, T, and N, P, and K, E? Okay, H hyperparameters, that makes sense. Yeah, we have learning rate, epochs, weight decay. But now this scares me. I feel it's equations like this that motivated my math revisions. Probably, yeah. Like, yeah. To an extent, even like the fast AI lectures, the was it Carnegie Mellon? Professor Graham, his lectures. Where does he teach again? Anyway, and all of that have some sort of, okay, we're going to do something with math. Did I lose internet? I hope not. I truly hope I did not just lose internet. Okay, I'm gonna assume I did not. Like, you think school problems are maybe okay, then you see papers, equations that are a bit scarier. Absolutely. And then you remember whether it's multiple limits or, yeah, other less simple cases. Yeah, definitely. Paper, like, equations are always scary to me. It didn't even. Okay, no, knock on wood, no, not a single freeze. Yes. Aaron, are you a math person? Good, I'm glad we're still here. Yeah, Ethernet for the win. Yeah, so. I remember liking limits in high school, but I don't remember anything about how it needs to be solved. I mean, I'm gonna maybe play a bit more to see what he's going to talk about in this slide, but then I'll most likely pause because I need to go in a bit. So let's see what he is going to talk about.
To the number of ensemble members that we have. And H is sort of a shorthand to denote like sort of the minimum over like all of the hyperparameters we're considering, which in this case is like learning rate, weight decay, and epoch count.
Just like math's assumption, let's assume I didn't lose internet. And that's what I did. Because I'm like monitoring, nothing is going red. That's good. Everything is green. Yay. Don't worry, enjoy the rest of your day, Ciela and everyone. Thanks. I still want to finish this slide. Because I'm curious if he will talk about the equation more or not. Because we see something about double limits.
And so if we compute this if we can estimate this double limit, this sort of characterizes the best possible performance of what we're going to call a joint scaling recipe as we send sort of both of these quantities to infinity. And so
to infinity and beyond.
Concretely, we sort of introduce a way to like estimate what this limit should be equal to. And the way in which we're going to do this is we're going to first take the inner limit. And so taking the inner limit here corresponds to sending the number of ensemble members to infinity for a fixed ensemble.
When we say we're sending it, not beyond, when we're saying sending it to infinity, does that mean because we have infinite compute, so we're just gonna let it go? Like, what does that even mean?
Member parameter count and a fixed data set size, where we're selecting our hyperparameters to give us the ensemble with the best possible asymptote. And so we sort of introduce like a heuristic to estimate hyperparameters that give you this best possible asymptotic performance. And so if you look on the plot on the left, what this is showing you is at this 200 million data size that we're considering, the x-axis here is the number of ensemble members, the y-axis here is our validation loss, and the different colors correspond to ensembles with different member parameter sizes. So the dark blue color corresponds to ensembles with 150 million parameter members, then 300, 600 million, and then 1.4 billion parameters. And for a fixed member parameter size, we can scale the number of ensemble members, and we can fit a power law to these losses. And so you can see that sort of even as you increase this member.
So these are different models and then different number of ensemble members. How are we taking it to infinity?
Parameter count, the power law fit is pretty clean. The exponents all look pretty similar, but you get an increasingly better asymptote. And so once we sort of have an estimate for this inner limit for different values of n, what we can now do is we can back out sort of the asymptotes of.
Oh, wow. So they kind of estimate the limit from infinite experiment extrapolations. Huh, if I recall. So I got the feeling it is maybe slightly unprincipled, but seems reasonable. My brain wants to stop, but
each of these individual power laws. So for this first power law for the 150 million parameter ensembles, we can estimate its asymptote. And then we can do this for each of the other parameter size ensembles, and this will give us 4 individual asymptotes, which are the points on the right. And once we have these 4 individual asymptotes, we can fit a second power law, which corresponds to sort of the second limit and the original double limit we introduced in the previous slide. And the asymptote of the second power law sort of characterizes the best possible performance of the joint scaling recipe. So there's a question which says, this graphic is already with the optimal number of epochs or single epoch. So yeah, each point here is sort of trained with like the optimal number of epochs to give you like sort of the best possible ensemble. So it's like not a single pass setting. And for sort of the specifics of like what this like heuristic hyperparameter recipe looks like and the exact values, you can see like the appendix of the paper where we kind of like detail all of this.
Okay, I'm gonna pause now because I'm mostly lost. Oof. Interesting. Sometimes I'm so thankful for such smart people to exist in the world. And I will live happily to not be one of them. I don't mind. I would like to assume I'm a smart person, but like not to that level. So I hope we did okay today. I hope brain is exploding. I mean, I would like to think I'm reasonably. I mean, I've said this before, but I like me thinking of myself as a smart person is like setting expectation for myself, which I know I do. So I would like to think within a reasonable limit, you know? I mean, hold up. I think we have a noise for that, don't we? Do we? Do we not? Anyway. Hold up. See? We do.
My brain hurts!
That was really
Code
loud.
Life will just redeem My Brain Hurts. Monty Python Gumby.
I redeemed it so that yeah, it's called My Brain Hurts, and I do feel that sometimes. But yeah, thank you for enduring today's stream. Have you tried the website called LeetCode? Yes, I have. I've tried it and solved 7 problems. That's amazing. Congratulations, really. So it is a website that I have frequented. It's not a website I use a lot, even though it would be pretty cool. Like I have done coding competitions, but not like the ones that are on LeetCode. I mean, that was Hashcode, not LeetCode. Hashcode is a Google thing. LeetCode is its own thing. But I do have, I think I both collaborated with Z and Chat with LeetCode. And those were some stressful things. Yeah. It's fun though. Fun and stressful. Is my voice going away? It's like on its way out. Yeah. So that was, I'm happy I was able to do Friday and Saturday stream. I know I was feeling like, do I want to do today's stream? But then I was like, why not? I get to talk to nice people. I'm a nerd in the coding world, but I have designed and coded my first ever web app. That's awesome. That just fetches data from the weather API. So you created an Android app? Or was it? Oh, you said web app. That's pretty cool. If you feel like it, you can like even share screenshots if you feel like it on Discord. We can encourage you. Or if you have any questions, even if it's in the chat, we can help you understand. I may not be the coffee, you know, my stuff doesn't work. I don't have my commands set up as well, that perfectly. Oh, hold up. Doppler effect going on. Huh? What do you mean? Discord link in Twitch bio. There we go. Probably, yes. What Doppler effect? What is the Doppler effect? So yeah, I will do my best to answer your questions, but I know we have smarter people. I think ReadyBot is out. But now, lol. Now I'm chilling here with you. What? That is... Oh, our bot. Well, yeah. What's going on in the stream? You can talk to ReadyBot? I didn't know that. It's a language model? That is so cool. What? I didn't know that. Anyway, I should... Does it answer? Oh my god. That is cute and creepy. I actually discovered you because you did a podcast with Free Code Camp. Yay! thank you. I think just saw its name, but it's also reading our messages. I mean, yeah, our messages are public, so yeah. Thank you for being here, Abed. And again, I really hope that nobody feels like a hostage in my streams. I'm glad you're here. My voice is fading. What is going on? My voice is fading or your voice? Aaron, are you okay? I can see you, Aaron. Don't think I don't see you just because I'm interacting more on the Twitch side. I see all. Okie dokie, I'm gonna go now and have breakfast. I expect bots to like ignore messages that don't start with a command. Or character. Maybe for oh yeah. That is a good point. I know Twitch itself does a lot of filtering for bad words. Okay, I'm gonna go to the goodbye pose and wish you all a lovely rest of your day. And yeah, I hope you had a nice time. It's called the Doppler effect. True, yes. True. True. Yes, I wish you a lovely rest of your day with anything you have planned and a lovely weekend. See you next time, inshallah, if it happens. Yes, Asher. I'm glad you're here. Thank you. Happy to have you. I appreciate you all. I really do. Like just the fact that also goodbye, Abed. Yeah. I appreciate that anyone who Michael is here. Anyone who watches the streams or interacts with me, even if it's for 1 minute. I appreciate that. Peace. Bye all. Have a lovely day. Catch you next time. I'm going to go to the end screen now. Yep.